12.7, we're going to be looking at max-min problems. So this is more like the applications of the calculus now. But to begin with, we've got this problem 1 here, and it looks fairly standard routine, just like we did in 12.6. However, we've got decimal points involved, and it's very clear that we need to show all the important features using exact values. I'm going to make use of the CAS calculator. So let's first of all put in our function f of x with that domain restriction in place into our CAS. So menu, actions define, and I've got f of x is going to equal 0.2 being multiplied by the bracket x minus 1 to the power of 2 being multiplied by the bracket x plus 4. And there's a domain restriction there, so it's given that x is going to be between -5 and 2. And with the original question had square brackets, meaning it's inclusive, so I'm using the inclusive symbol. Alright, it's defined. Now, because I can use my CAS and I just have to show those key features, you might be thinking, well, all I need to do is do a sketch of it, and then I can just use my max-min functions within the graphing area. So if I go to the home screen and start generating a graph, and I'll do f of x, there you can see it. Okay, that looks all good. So I wonder where this maximum is, so I could go menu, analyze graph, and go maximum, and I'll start from the left hand side, go to the right hand side, and there's my maximum. The key to this is that in the question we need exact values. So sketching the graph and then putting in finding the maximum in this approach is not helpful. Instead, what I need to do is go back into the calculator mode and start making use of what we did previously. So y-intercepts, where do they occur? It's where x is equal to 0. So let's have f of 0. Whoops. And you can see it's equal to 0.8. Now it's going to give me a decimal approximate. So what I should do now is put my calculator into exact mode. Menu, home screen, settings, and I want document settings. And you can see that I've got my answers in auto. I'm going to select exact. And then go back into where I was. And now let's evaluate f of 0. And I get the 4/5. Now notice that 4/5 is in fact exactly equal to 0.8, but I am now going to have all my answers in that fractional format. So for this y-intercept, all I need to write down in my written response is y-intercept x equals 0, f of 0 equals that, so I have the 0.0, 4/5. X-intercepts occur where f of x is equal to 0, so I just write that down, and then write down the solutions for x, and then finally the points. On my CAS, I'm going to be making use of the solve function. So menu, algebra, and solve. I'm interested where f of x is equal to 0, so y equaling 0, and solving for x. You can see it's a -4 and 1. What are their corresponding y values? F of -4 and f of 1. And so you can see I have those there. Now they were x-intercepts, so I didn't even need to do that on my CAS. Endpoints, I've got between x equaling -5 and x equaling 2, so f of -5, and notice it gives it to me in exact format, and my other endpoint is x equaling 2, so f of 2, and there it is again, exact, 6/5. So I've got my endpoints. I also need to consider the turning points. So remember the stationary points occur wherever the derivative is equal to 0. So, on my CAS, menu, algebra, solve. I now want to bring up the derivative function. So menu, calculus, derivative. I'm doing it with respect to x. I want it to take the derivative of f of x. I'm interested where that is equal to 0. And I'm solving for x. And you can see I have those two values. What are their corresponding y values? So I'll have f of the fraction, -7 on 3. There's my exact value, and also f of 1. So now I have all of the information that I need. So there's my turning points. I can also go through and work out a sign diagram here. So I've got my x, and there's my first turning point, -7 on 3. I can choose a value a little bit to the left and a little bit to the right and work out the derivatives for those. So this ends up being a positive value, so I know that the shape will go up towards the right. If I substitute 0 into the derivative, I'll get -7/5. That will go down towards the right. I've extended this sign diagram to cover the other turning point, which occurs at 1, 0. But if I substitute the 1 into the derivative, it will produce a 0, as it should always do for a turning point, which will mean the shape will be flat. On the left-hand side, I had a negative value for the gradient, so that went down towards the right. On the right-hand side, and I just nominated 3 on 2, then that produced a positive gradient that went up towards the right. How is it that we got 23 on 20 and all of the others for that matter? Is following that kind of syntax. So just to show you, I'm going to evaluate the derivative of f of x given that x is equal to 3 on 2. So menu, calculus, derivative with respect to x, and it's f of x. And then on the outside of this bracket, it's given that x is going to equal 3 on 2. Hit enter, and you can see I get exactly 23 on 20 for that derivative, which is here, which of course is positive. So I now know that I have a maximum here and a minimum there. Time for the sketch. My endpoints, my local maximum, my local minimum, the y-intercept, the x-intercept, and that is also an x-intercept. So just a reminder, you don't need to show a heap of workings for this. What I've got here in red is all you need to show as your response in a CAS-enabled question, and I've given you the steps of what to do on your CAS calculator itself. Alrighty, so right now we're going to be looking at max and min application problems. This is really the exciting stuff for me anyway. It's where we get real life problems and we're able to find solutions using calculus. So these are the steps that we should follow whenever we have a max-min application problem. Firstly, the question will be given to you in a written format, and what you need to do is to be able to convert that into some kind of mathematical statement or equation. You then want to find the values of x for where the max or min occurs. So basically, work out the derivative of the function, make it equal to 0, and solve for x. We then want to make use of a sign diagram to establish whether we're dealing with a maximum or a minimum. And of course, we substitute the found x values into the original rule to work out what the actual maximum or minimum values are. And then number 5 is where we apply some logic. Is the solution that we've come up with within the parameters of the original question? Does it make sense? For example, there'll be no point coming up with a moment in time that is in fact negative, because we can't go backwards. In the same way, there's no point coming up with a solution that produces a negative area. We just need to be practical. All right, so this is our first real application question. Here in problem 2, we have this farmer. Here's enough fencing to make a rectangular pen that has a perimeter of 200 metres. What dimensions will give an enclosure with a maximum area? So obviously he wants the area to be as large as possible to contain his animals. Just ignore the x's and the 100 minus x here in this diagram, but we'll just start off with a rectangular shape. What we know straight away is that the perimeter, the length of the entire fence, is going to be 200 metres. Now if we look at that rectangle, then it's going to have two unknown lengths and two unknown widths. If I just determine the width as being the variable x, I can write that the perimeter is equal to 200, which is equal to 2l plus 2x. So I've just let the width be an unknown x. If I go back to our diagram, you can see I've set the width as being x. Continuing on, if I divide everything by 2, I'll get this line here. And then finally, if I subtract x from both sides, I'll get 100 minus x equaling the length of our rectangle. So that's how I come up with 100 minus x. Now remember, the objective here is to find the maximum area. So I can come up with an area rule. So area equals length times width. The width is the x and the length is 100 minus x. And then if I expand that out, I'll get that the area is equal to 100x minus x squared. Notice that we have an area function with only one variable, that variable being x. With all max-min problems, what we do next is take the derivative, make the derivative equal to 0, and then solve for x. So you can see I've got dA dx, change in a over change in x, equaling 100 minus 2x. I make that derivative equal to 0, and then I finally solve for x, and I see that x is equal to 50. That should give me the maximum area. I now create myself a sign diagram, and so I put in the 50, and of course if I substitute that 50 into the derivative, I'll get a 0, and that will mean that there's a flat shape there. I'll choose a value to the left, so something easy to calculate, and I chose 40. So if I substitute 40 into the derivative, then I'll get 20, and that's positive, so that means that the shape will be up towards the right. A value to the right hand side, 60, that produces negative 20, so therefore down towards the right. And because of this shape, I know that I have a local maximum. Finally, what is that maximum area? What I need to do is substitute the found x value into the original rule. So area equals x times 100 minus x, substitute 50 in for x, and you can see it's 2,500 meters squared. So when the width is 50 meters, a maximum area of 2,500 meters squared is achieved. In this question here, what we do is we begin with a flat piece of cardboard of 10 centimeters by 6 centimeters, and there it is shown here. We end up cutting out 4 squares from each of the corners to create some tabs that can be folded up to create a box, which will obviously have some kind of volume. And this is to do with a jewelry shop, so it's going to contain rings and necklaces and whatnot. The objective here is to make sure that that volume is a maximum volume possible. So the question for us is, hey, how big should these squares be so that we obtain a maximum volume? Now let's start with the width. The width here of the piece of cardboard is 4 centimeters. If I'm cutting out an X on the right and an X on the left, then it's clear to us that the length of this tab here, which will represent the floor of the box, will be 4 minus 2x. Along this side, then we're going to have the 6 centimeters taking away x here and x there to mean that the length of this tab will be 6 minus 2x. And of course, if you can imagine that those tabs are all now folded up, the height of the box is going to be an unknown x centimeters. So we'll begin with a volume function, so v of x is equal to length times width times height. But instead of writing L, W, and H, I'm going to write them in terms of x. So the length of the box is going to be 6 minus 2x. The width is going to be 4 minus 2x. And then the height of the box is going to be x centimeters. So you can see now that we have a volume function which only has one variable in it. In all these max-min problems, what we want to do is work out the derivative of the original function, make it equal to 0, and solve for x. We'll then get those found x values and substitute those into the original rule to produce what the max or min is. And we'll also make use of sign diagrams. Okay, so using your CAS, v prime of x equaling 0, you can see that x is exactly equal to these solutions, which is approximately equal to 0.78 or 2.55. So we've got two possibilities here, according to the rule. Remember, to obtain these exact solutions, you need to have your calculator in exact mode for the answers. Now, whilst there are two possible solutions, and we could create a sign diagram and see which one produces the maximum, we also need to think about the real world. Are both of these solutions possible? Let's look at the restrictions for this. Clearly, what we want to see is that all of the lengths are greater than 0. So the height needs to be greater than 0, otherwise we won't have a volume. The width, 4 minus 2x, needs to be greater than 0, and the length needs to be greater than 0 as well. Let's deal with the 4 minus 2x. Add 2x to both sides, divide both sides by 2, and you'll see that x needs to be smaller than 2. Looking at the length, 6 minus 2x is greater than 0, and you can see that eventually x needs to be less than 3. So x has got to be greater than 0, less than 2, and also less than 3. So really we don't need to worry about the 3, because the true restriction is to say that x is greater than 0 but less than 3. So we're looking for the domain of this. Notice that we're not including 0 and we're not including 2, because if we achieve those particular exact values, then the volume itself would be 0. So that allows us to dismiss this solution here of 2.55 because it's not within the appropriate domain. So the x value is exactly 5 minus square root of 7, all of that being divided by 3, approximately 0.78. Let's verify that it's a maximum. So we create ourselves a sign diagram. We're interested in 5 minus the square root of 7 over 3. If I substitute that into the derivative, I should get a 0. And of course, that'll be flat. A value a little bit to the left, and I chose 0. That produces 24, which is positive, so the graph goes up towards the right. Subbing in 1 into the derivative will produce negative 4, and that's negative, so that goes down towards the right. So you can see the shape, up, flat, down. Therefore, we know that we have a maximum turning point. If I now substitute that found x value into the volume function, you can see that it's exactly equal to this solution here. That's the maximum volume that's achievable, which is approximately 8.5 centimetres cubed. A small organisation in Bowman Court have a need to produce boxes. And in that box, we don't know what they're going to be placing, but probably looks a little bit sus to me. But the size of the boxes, the volume of the box needs to be 27,000 cubic centimetres. The ends of the boxes are going to be square in shape, so it's a W by W, and these W's are unknown. And then we have an unknown length. Now with the cardboard, to keep everything together, we're going to pack it with tape. And that tape is going to be thrown over the cardboard in this fashion. So along the length, just one beam of tape. And then across the width, you can see that there's 2. All right, A, express the length of the box, L, in terms of W. So we want to come up with an equation that says that L equals such a rather W. So we start off for A that the volume is equal to W squared, which is just the area of the square of the box. So we're talking about this part here, W times W, multiplied by the length. That will be the volume. The volume in the question was set as being 27,000 cubic centimetres. So we have 27,000 equaling W squared times L. And now I simply divide both sides by W squared. So L is equal to 27,000 divided by W squared. Part B, Write the formula for the total area of cardboard in terms of W. So you want the total area here. So area is going to equal 2W squared. So we're going to have that face there. So there's that one, which is W squared, but there's also going to be, if you can imagine, another one at the very end here of the box. Plus 2LW. So if we consider this face here, the front, and we're also going to have the back, and that dimension will be L times W. And then another 2LW. If you can imagine the top of the box, so it's an L times W, and then also that's going to be repeated at the bottom. So altogether here, the area is equal to 2W squared plus 4LW. Remember, we want the area to be expressed with only one variable. At the moment, at this line here, we have two variables, L and W. But from A, we know that L is equivalent to that. So let's rewrite it so that instead of containing L, we've got 27,000 over W squared. That's what we've done here. So I have 2W squared plus 4 times 27,000 gives me 108,000. And W squared at the bottom and a W up the top will just give me with one W down the bottom. And in the final line, I've just reorganized things so that it's in a way that I can easily find the derivative. So I've just brought that W up to the top and written it to the power of -1. So now I have area is equal to 2W squared plus 108,000 W to the power of -1. C, find the dimensions of the box that uses the least amount of cardboard. So we want to obviously keep cost to a minimum. So this time the area is equal to this. I can come up with a derivative for the area. So change in area over change in W is equal to this. And I can factorize that. So I have 4W being multiplied by 1 minus 27,000 W to the power of -3. So if you can just imagine I've taken out W as a common factor for this part here, then I can write that as being W to the power of -3. So there's my derivative in factorized format. So 4W equals 0, or that there equals 0. So you can see W ends up equaling 0, or W equals the third root of 27,000. So what number, when multiplied by itself 3 times over, gives me 27,000, and that's 30. Please note that it's not a positive and negative. We're taking the third root, so it only has one solution. Now, the question did ask us to find the minimum. So write down, find the dimensions so that we have the least amount of cardboard. So we're talking about the minimum. So I come up with the sign diagram. So W, I've got my 30. If I substitute that into the derivative, it will give me 0, which will be flat in shape. Choosing a value to the right-hand side, I chose 31. If I substitute that into the derivative, I get 11.62. Obviously, I've done that with the CAS. And the shape will go up towards the right. Left-hand side, you can see that the shape goes down towards the right. Therefore, I have a local minimum. And that W equaling 30 produces a minimum. So what's the length then? Remember that the length was going to be equal to 27,000 over W squared. Let's substitute W equaling 30 into it. And you can see that that produces a length also of being 30. Now, if I substitute W equaling 30 into the area, you can see that we achieve an area of 5,400 centimeters squared. So now what I know is that a 30 by 30 by 30 centimeter box uses 5,400 centimeters squared of cardboard, and this is the minimal amount of cardboard that are required to achieve a volume of 27,000 cubic centimeters. So for part D, we're going to be taking a look at the length of tape. And what we need to do here is to write a formula for the total length of tape in terms of W. So you can see here that if I consider the front of the box, I've got 2 W's. as far as the tape is concerned. If I consider the left-hand side of the box, I've got 1 W. Obviously the right-hand side, which you can't see, another W. The top will consist of a L and 2 W's. And the bottom will be the same. So basically we had 3 different faces here, but they are reproduced. So the top and the bottom, left, right, front, back. For D, the amount of tape will be 2 lots of W. So that's from the from the left and the right. Plus 2 lots of this 2W. So that's the front and then the back. And 2 lots of 2W plus L. So a W, W, and L for the lid, and then that's reproduced at the bottom. So that's why we've got the 2 there. This ends up becoming 10W plus 2L. Remember earlier from A, L was equal to 27,000 over W squared, so I can just replace that. I now have a rule just containing W as the variable. And of course that W squared on the bottom I can bring to the top and write as W to the power of -2. And the reason for that is it makes it very easy to work out the derivative. So there's my rule. Part E, find the dimensions of the box that uses the least amount of tape. So we're talking about the least amount of tape, so we're looking for a local min. So change in tape over change in width is going to equal 10 minus 108,000 W to the power of -3. I make the derivative equal to 0. And now I look at solving for W. And you can just do that on your CAS at that stage there. Here I've shown all of the steps through it. And we end up being that W is equal to the 3rd root of 10,800, which is approximately equal to 22.1 centimeters. Just to create a sign diagram to verify that that is in fact a minimum, I start with my found W value, sub it into the derivative, it gets a 0, so of course it's flat. A value to the right hand side, I chose 23, produces up to the right, so it's going up there. And to the left hand side goes down towards the right, so the shape I get is down, flat, up. Therefore we have a local minimum when the width is equal to the 3rd root of 10,800. Alright, so what does that mean as far as the length is concerned? So here's my length rule containing W. I substitute the found W value into it, and you can see I come up with exactly that expression, which is approximately equal to 55.26. What is the amount of tape that would be needed? So here's my tape rule. I've substituted the found W into it. And this is what it's exactly equal to. It doesn't simplify any further for us, which is approximately equal to 331.56 centimeters. So when the dimensions of the box are 22.1 by 22.1 by 55.3 centimeters, a minimal amount of tape of 331.6 centimeters will be used. And the package, of course, will contain 27,000 cubic centimeters as far as the volume is concerned, which was set at the very beginning of the question.